My task is to make a simple inverting amplifier on Tinkercad. Okay. And let us say it says, let the gain of this amplifier be -5. Okay. That means I only know gain. The choice of resistors is completely up to me. Now, what do we know about an inverting amplifier? We know that the gain of such an inverting amplifier is RF upon R1. And the circuit is something like this. Right? You have negative feedback. So this is inverting terminal. It's an inverting amplifier. That means I'm going to give input to the inverting terminal as well. Non-inverting terminal is grounded. This is R1, this is RF, this is V0. Note that in general, when we draw any circuit of op-amp, we do not explicitly every time draw VCC and VEE, but it is implicit and understood that VCC and V minus VEE are connected. Okay, only then this any op-amp circuit is going to work. An op-amp circuit will not work unless you power it. But these need not be shown in every circuit. Okay, that's why we skip it. But now that we are making physical connections, let me show that there is a plus VCC and a minus VEE. Let us assume that this will be plus 15 and minus 15 volt. Okay, now to obtain a gain of -5, I can choose any resistors, right? So I'm going to choose simple values. Let me say that I'm choosing RF to be 5 kilo ohm, and as a result, R1 should be 1 kilo ohm. Okay. I have chosen these values. Note that these right now, just for the sake of simulation, these may not be standard values of resistors. If you remember in an earlier class, I have requested you to go through E6, E12, E24 series of resistors, right? These are the standard families of resistors. What do they mean? What are the values as a part of these standard values of resistors? Please make sure that you understand this. Okay, please read up about them. Because if you go to the market and simply ask for give me a resistor of 113 ohms, you will not get it. Okay, you will not get it. There are certain standard values of resistors, and only those values would be available, and these standards are made so that there is a uniformity across manufacturers as to what kind of resistors or what values of resistors will they manufacture. Okay, so please keep in mind the standard values right now from a simply from a simulation point of view. Because it says gain is 5, I am simply taking R1 as 1 kilo ohm and RF as 5 kilo ohms. But if you were physically making it, please make sure that both these values should be available in the market. Okay, should be some standard value. So if these are not 1k is a standard value, find out if 5k is a standard value or not. If it is not, then you have to redefine or re-choose the values of R1 and RF which are available in the market so that you can actually purchase them, right, to make such a circuit. For example, right now I'm just taking it as 5 and 1, which would give me a gain of -5. So this is the target. Okay, this is the objective. Now let us make this circuit in Tinkercad. So let us recall what terminals these are. Inverting terminal is terminal number. What is it? 2. Okay, so this is 2 and this should be 3, right? Okay, VCC is 7, VEE is 4, and Vout is 6. Okay, so these 5 terminals are what we are going to use. So let us go to Tinkercad and now make this circuit. So I'm going to start, take a breadboard, Okay, and I need op-amp. So operational amplifier. If you search with op-amp, you'll not find it. You'll have to write operational amplifier. Okay, I've got 741. Great. This is the IC I was looking for. Okay. Now let me rotate this and rotate this as well. Now it's kind of very easy to make out which is top and bottom here. It has the groove cut, semicircular groove cut, as well as the dot. Because this is a simulator, it also has all these points. These terminals are actually labeled also. Okay, so there is no point of any confusion here, but this will not be the case in a real IC. Okay. So, okay, so what all do I need? I'm going to take this op-amp and place it here. Fine. Going back to the circuit, I need to ground I need to ground what? Non-inverting terminal, right? This one has to be connected to ground. Okay, so let me define these two rails are already there, right? So let me bring in my DC power supply, which is actually going to power my circuit. So I'm going to write power supply. This is it. Okay? This is a DC power supply. So this is what my VCC will be, and this is what my VEE would be. Let me now assume for a second that I'm using a AC input. This input that V in that I have drawn, let me assume that it's an AC input. Okay. So let me also bring in a function generator. This will be my function generator. Okay. And the input, okay, so I'm going to make those input and output values at the end. Let me quickly make the circuit first, right? So I need an R1, and R1 we had decided that we will take it as 1 kilo ohm, right? So let me, this is already 1 kilo ohm. Let me rename it as R1. Okay. R1 should go between what and what? R1 goes between, I can't hear you, sorry. Input and 2. Input and input and 2. Okay, so that means I have to make, say I have to give input somewhere. This is input number 2, right? This is V in non-inverting terminal. So this is where my input should come, right? So let me take this function generator, and already, so this is going to be my input. This is input and this is the resistor. Let me take this moment to also define a ground. Okay. But I need a common ground. Okay, so let me just take it here. Maybe it will be better if I take it around. Okay, this is going to be my ground terminal. And this is my input. Fine, V in R1 is connected to inverting terminal. Next, what do I need? I need RF. RF should be 5 kilo ohm. Let me call it RF. This should go between what and what? 2 and 6. Okay, so 2 and 6. So I can't bring it from here. So let me just connect it somewhere here. Okay, and this needs to go to 2. Is that right? And this needs to go to 6. What is 6? Output, right? What this is output. Okay. This is done. Let me change the color of the wires. So this is say red. Okay. So I've connected R1 to input. I have connected RF between 2 and 6. This was 6. Now let us connect the display devices. We'll connect the sources at the very end. Okay. So I need oscilloscope. I need an oscilloscope. Note that you need an oscilloscope only and only for analog signals. Okay, if this was a DC input, If this was a DC input, then you won't need an oscilloscope, because oscilloscope will just show you one DC value, right? So there's no need for oscilloscope there. If you were, because I'm choosing an AC input right now, I'm using an oscilloscope to display the waveform. Otherwise, there is no need for an oscilloscope. You can simply do with a multimeter. Okay, so this is going to show my output. Let me also put some annotations here. So this is my V in, and this is my V out. Okay, now I need to measure output across what and what? Across ground and V6, pin number 6, right? That is this. Is this correct? Yeah, this is V out. And the other one, I'll take it to ground. Note that I'm just assuming this is ground terminal. I have not made it ground yet. Okay. When I connect these supply voltages, that is when I actually make it ground. Okay, so this is going to show my output. Let me also make connection so that I can see the input. So let me just directly connect my function generator with the oscilloscope. So oscilloscope also has to have the same ground. We have to always ensure that there is only one ground. Okay, there should be always only one ground in the circuit. There should not be multiple grounds in the circuit. So this is my ground. This will show me my input voltage. Let's take yellow. Let's take this also as yellow. So I have everything is fine. I've made arrangements to display input voltage, which is coming from the function generator. I've made arrangements to display the output voltage, right? Now all I need to do is just power this circuit. Everything else is done, right? Is there anything left? Pin number 3, that is input. Yes, this needs to be connected to ground, right? So I'm going to take a wire from here, make it turn and go here. Right. Now it's done. Right. Now all circuits have connections have been made. Pin number 3 is connected to ground. Now I need to connect supply. So let me put a label on this one. And I'm saying this is going to be my VCC. And what should be VCC? VCC should be plus 15 volts. Let it give a maximum current of 3 amperes or 1 ampere, whatever. We're not interested in how much current it should give. By default, it says 5 volt. This, okay. Now I have connected I have made VCC. VCC has 15 volt. Okay. So I'm going to make a connection. This is my positive rail. And this is my ground, right? This is what I called earlier grounds. Okay, black. And I'm calling this as red, just for reference. Now, where should I give VCC? To pin number 4, right? No, 7. Okay. This is 7. Okay, so I just need to connect this with this. Is this correct? Pin number 7 connected to plus VCC, right? This is pin number 7. Okay, and this I have connected to ground. Okay, now note that my plus VCC part is done. Okay, but how to get minus VEE? To get minus VEE practically, what you can do is just make this also as a 15 volt supply, okay, 15 volt and 3 ampere supply. And now instead of connecting red terminal to plus and ground to ground, let us just invert the terminals. Okay? That means I need to connect VEE, minus VEE where? To pin number 4, right? So let me bring this and make a rail over here. Let me call this as red. And now let me connect the negative terminal to this terminal. I'm considering this to be positive. Are you understanding what I'm doing? I've connected the negative terminal of the supply voltage to VEE, and now the positive terminal of this DC power supply, I'm going to take it where? I'm going to take it to ground, right? And this is what is my ground terminal. I'm going to turn it black, and I'm done. Now my circuit is complete. Let me add a label that says this is minus VEE. This is where before starting simulation, I had to select the input waveform, right? So let me just say I'm choosing a sinusoidal input function generator. I'm naming it Vin. Frequency is say 100 hertz, just for example. Input amplitude is 5 volt. Okay, let me make the input amplitude as say 0.05 volt, just for example. And I want no offset, so I want 0 offset, and I need the function to be sinusoidal. Okay. Starting simulation. Now you notice the oscilloscope is giving me this kind of an output, right? Why is this? Because my scale is not matched yet. Okay, my scale is not, means there are too many cycles for the scale which is currently showing. So the scale is currently showing me as time per division is 100 milliseconds, means one division is equal to 100 milliseconds. I need to reduce this, because what is the frequency of my signal? 100 hertz, right? That means 100 cycles in 1 second. So you notice that when I decrease the time per division to 10 milliseconds per division, now I am able to visualize this much better. If I reduce this further, let me say this was 5 milliseconds. Oh, for this one, 5 milliseconds. You notice the waveform has become slightly spread out. Okay, so I'm going to keep it as 10 milliseconds. This is fine. And if you look at it closely, what does this show you? It says that this entire scale, that means 1, 2, 3, 4, 5, there are 10 such units here. This is equal to 100 milliseconds. Okay, that means one division is equal to 10 milliseconds. If I had changed this value here, when I made it 5 milliseconds, you notice now this whole 10 division is equal to 50 milliseconds. That means one division is equal to 5 milliseconds. How about I used a DC input? Okay, so instead of this, let me okay, so I'm taking a DC input, and now instead of oscilloscope, what should I use to make measurements? Multimeter. Okay, so let me take it as say 1 volt. Okay, DC voltage 1 volt. This is my V in, and now I'm going to bring a multimeter. So, okay, just to clarify, what we have drawn earlier is absolutely correct. Okay, there is nothing wrong in what we have drawn earlier, but we could not observe inversion there because the oscilloscope does not have those features. The oscilloscope in Tinkercad is a very basic oscilloscope. Okay, you do not have a trigger value, you do not have a zero instant, which is why I'm now saying, okay, let us do it in DC and see whether what we've done is correct or not. So I'm saying let us take a DC input of 1 voltage, and I'm going to measure the output on multimeter. Rest everything is same. So if I start simulation, so our calculation is absolutely correct. This is black, right? We gave 1000 millivolt as the input, which is 1 volt. This is what we gave as the input. And when I'm putting my multimeter across V out with respect to ground, I'm observing -5. Yes, it's correct, because we designed a circuit which should have a gain of -5. Okay, the choice of these resistors was completely up to you. You could have chosen any values, any standard value of such resistors. You just need to make sure that the ratio of their values should result in a gain equal to -5. This is another very important advantage that op-amps offer to us. Okay. And that is that the entire gain now depends on the ratio of resistors and not on the value of the resistance as such, right? So all I need to do is maintain a particular ratio of resistance values. Doesn't matter what those values are. You're saying you wanted a signal like this. Okay. This is 5 volt. This is 2.5 volt. Okay. So theoretically speaking, the peak value of this signal is 5 volt. And what is the DC offset? 2.5 volt. Right? बट सो फिजिकली जब आप ये फंक्शन जनरेटर में कर रहे होते ये सिग्नल जनरेट करने के लिए, ऐसा सिग्नल जनरेट करने के लिए, तो आप यही करते, आप डीसी ऑफसेट 2.5 रखते और पीक वैल्यू 5 वोल्ट रखते. लेकिन फॉलस्टैट सिम्युलेटर में जब आपको ये करना होगा तो आपको कैसे करना होगा? आपको लिखना होगा कि डीसी ऑफसेट is 2.5 and you will have to say that VP is also 2.5. क्योंकि फॉलस्टैट सिम्युलेटर क्या करता है, इस एवरेज वैल्यू पे आपने जो भी पीक वैल्यू बोली उसको ऐड कर देता है. Okay, so just on Falstad, if you were making this, if you wanted to generate this kind of a signal, you would have to say DC offset is 2.5 and peak value is also 2.5. Then it will generate a signal like this that goes all the way up to 5 volts. Okay, but if you were doing this in a practical function generator in the lab, you would have simply done this. Would have been sufficient. So you need to change how you define signals based on the simulator. So this E6, E12, E24, let me just tell you the basic funda behind it. Okay. So what does this 6 and 12 and 24? This is like a standard that manufacturers have decided, which says that, you know what, we'll not have every possible value of resistor. Means ऐसा नहीं है कि 1 ohm भी होगा, 2 ohm भी होगा, 3 ohm भी होगा, 4 ohm भी होगा, ऐसा नहीं होगा. What they've decided is that if they're following E6, that means in a decade means value from 1 to 10, they will divide this interval into 6 equal parts. There is an E3 series also, which would mean that 1 to 10, 1 decade, will be divided into 3 equal parts. Okay. So, and then what will happen? 10, iske baad next kya aayega? 100. So do you notice that I'm looking at a logarithmic scale now? So if this is 1, this is 10, this is 100. And so on. So 1 ohm exists, 10 ohm exists, 100 ohm exists, 1K exists, 10K exists. But if I was looking at E3 series, what would be the next value? So just on that note, if this is what I was doing, and I have to round it off also, right? So in E3 series, my manufacturer is going to give me 1 ohm, it's going to give me 2.2 ohm, and it's going to give me 4.7 ohm. And next value will be 10 ohm. And then the next value will be 22 ohm, 47 ohm, and then 100 ohm. The next value will be 220 ohm, 470 ohm, and then directly 1K. The next value will be 2.2K, 4.7K, and the next value will be 10K. This is how my E3 series of resistors would be defined. Okay. Which is why in many, when you look at these examples which are given in the book, right, and you notice that why are they using these weird 3.3 kilo ohm, 4.7 kilo ohm? Why do they use these kind of values even in the solve examples? Because these are standard values. Okay,